Hello everyone, welcome back to this online class. Today we are going to look at the applications of first order ordinary differential equations, and in particular we are going to look at the orthogonal trajectories. Now first of all, we need to know what we mean by an orthogonal trajectory. What happens here? Remember, the word orthogonal means perpendicular. You need to take note that when you talk of orthogonal, it means perpendicular. So then what does the orthogonal trajectory entail? Here you are given a family of curves, so many curves. Let's say you are given this family of curves. We can say these are f of xy is equals to a constant c. That is a family of curves. The first family. Can indicate here that the first family. Now the task here is to determine another family of curves. Let me draw here. We need to determine another family of curves. These ones. I can call this g of xy is equals to a constant k. Let me comment on this. G of xy is equals to a constant k. So this is always given. You are given the first family, and your task is to find the second family. And the idea between these two families is that each curve in the first family intersects with every curve in the second family at 90 degrees. So, if you want to know, let's say we have taken these points. At that point, I can come up with the slope of the curve in red, the gradient of that curve in red, draw the tangent, and also the tangent to the curve in blue. So let's call this T1, and this tangent line is tangent line T2. The angle between those two tangent lines is 90 degrees. So it means every curve intersects with every other curve in the other family at 90 degrees. The angle here is 90 degrees for all those curves. So if I pick an arbitrary point P, let's call this P of xy. Is it possible to get the slope of those two tangent lines? We are going to say let, I can use another color, that let M1 be the slope of T1, and the slope of that, let it be equal to dy over dx. M1 is equals to dy over dx. That is the slope of the tangent line T1. Also, let M2 be the slope of the tangent line T2. If you know M1 is equals to dy over dx, what about M2? I'll tell you how to get them. Now, at point P, you can write but T1 is perpendicular. That means perpendicular to T2 at point P, Pxy. What do we know about perpendicular lines? It simply means that the product of their gradients should be equal to -1. M1 times M2 should be equal to -1. That is the condition for those two tangent lines to be perpendicular, that the product of their slopes or their gradients must be equal to -1. So if I know m1 to be dy over dx, therefore, we can be able to find m2, which is -1 over m1. And so this is the same as negative dx over dy. That's m2. Now, look at the first family of curves. A function of x, y is equals to a constant c. We can be able to find the ODE corresponding to the first family of curves. So you can write this. That given that f of xy is equals to a constant c, it means if I differentiate both sides, I'm going to get differentiate both sides to get df, derivative of f, is equals to derivative of c, which is c is a constant, so the derivative of c is 0. Now df here means the total differential of f. And you can recall from differential calculus that when you have a function of two variables, like f is a function of x and y, when you talk of total differential of that function, it's the same as partial f with respect to x dx plus partial f with respect to y dy is equals to 0. You see, this one is an ODE. So this is the ODE for the first family of curves. So this one is the ODE for the first family of curves. Because when you solve it, you go back to f of xy is equals to c. But the task here is to find the other family of curves that we are calling g of xy is equals to k. So we need to know which equation do we need to solve to find g of xy is equals to k. Now, if I want to obtain the ODE corresponding to the second family, I will now replace, look at the slope of the second family. It is negative dx over dy. But the slope of the first family is dy over dx. So that means the slope has to change for the second family. So where there is dy over dx, I'm going to replace it by negative dx over dy. So I'll write here that to get the ODE, to get the ODE for the second family, replace dy over dx by negative dx over dy in the ODE for the first family. So let's do the replacing of those differentials. What does it mean? That where there is dy, I'm going to write negative dx, and where there is dx, I'm going to write dy. So it means here, this one now, dx will now give us dy, and where we have dy is negative dx. So that will give us the ODE for the second family. So we'll now talk of partial derivative of f with respect to x dy minus partial derivative of f with respect to y dx is equals to 0. So this is the ODE for the second family. So when you solve this, you obtain the orthogonal trajectories. So this is the ODE for the orthogonal family. So this is what you need to solve. Solve it to get, solve it to get g of xy is equals to k. So that is the idea about orthogonal trajectories. And these orthogonal trajectories are applicable in engineering and physics, especially in what we call the equipotential lines, the streamlines in an irrotational two-dimensional flow. Those are examples of orthogonal trajectories. So I want to give you a question that is dealing with orthogonal trajectories. And let's give you an example. You can write examples, or simply example one. Example number one. We can write, find the orthogonal trajectories find the orthogonal trajectories. That should be trajectories. Let me write that in a better way. Orthogonal trajectories of the following family of curves. In part A, we have x squared plus y squared is equals to cx. And in part B, we have y squared is equals to 4c times x. So let's find the orthogonal trajectories we are going to solve. Of course, what you need to take note of is that the ODE that you need to solve is this one. That's the one that we need to solve. So we need to find the partial derivative of f with respect to x and also with respect to y. Then you substitute into this ODE, solve it to get the required orthogonal trajectories. So part A, solution for part A. Of course, remember, f must be equal to a constant. The function f must be equal to a constant. Look at this. So you have to make C the subject. F must be equal to a constant C. So when I make C the subject here, remember we are given x squared plus y squared is equals to C times x. This means that I can divide by x on both sides to get x squared plus y squared over x is equals to C. Which simply means that if I simplify, I'm going to get x plus y squared over x is equals to C. So therefore, the left-hand side is our f of x, y. So this one is f of x, y. That should be equal to C. So you can say now let f of xy be equal to x plus y squared over x. Now I need to find the partial derivatives of f. So you can write partial f with respect to x Remember, you assume that y is constant, so this will give us 1 minus y squared over x squared. Another one is partial f with respect to y. Now you keep x constant, so we are going to get 2y over x. We only differentiate the y's. So now the ODE to be solved, our ODE for the orthogonal family. Look at the equation that you need to solve. It is this one that I've bracketed. So I'm going to substitute those partial derivatives. Fx dy minus fy dx is equals to 0. So it is this one, partial f with respect to x dy minus partial f with respect to y dx is equals to 0. So that is the ODE that we need to solve to get the orthogonal family of the orthogonal trajectories. If I replace the partial derivatives, what do we get? We'll have here 1 minus y squared over x squared dy minus 2y over x dx is equals to 0. So this equation, is it separable? You need to classify the equation. Of course, if I multiply by x squared, what will I get? I'll get x squared minus y squared dy minus 2xy dx is equals to 0. If you look at this equation, remember you can classify the equation into either of the 5 categories. It can either be separable, homogeneous, exact, linear, or Bernoulli. But if I look at the sum of the powers of the variables in each term, I realize that it is 2 throughout. 1 plus 1 here will give us 2. Again, here we have 2, 2. So this equation is homogeneous of degree 2. Now, how do we solve a homogeneous ODE? We make these substitutions. We say let y be equal to u times x, so that when you differentiate, you're going to get dy is equals to u dx plus x du. That is product rule. Now, let's substitute those values there, or simply y and the dy in the ODE, so that when you substitute, you get your ODE to be, now it will be x squared minus y squared, that is u squared x squared. This is dy, and dy is the same as u dx plus x du. Then minus 2x squared u dx, that should give us 0. You see, x squared is common. That can be factored out. So you can write all x squared into 1 minus u squared times u dx plus x du minus x squared times 2u dx is equals to 0. So when I divide through by x squared, this will cancel with this. And now we'll have now 1 minus u squared times u dx plus x du, then minus 2u dx is equals to 0. So I can now combine the terms involving the x You can see dx appears twice, this and also this one. Let's combine them into one term. So you can just write or u minus u cubed minus 2u dx plus x into 1 minus u squared du is equals to 0. Or, let me simplify. This is the same as negative of u cubed, then there's my plus u. Remember, u minus 2u, that's negative u, and the negative is common, so this is dx plus x into 1 minus u squared du is equals to 0. So this equation here is separable. It is possible to collect the x's and the dx on one side and the u's and the du's on another side. So this is separable ODE. If I separate the variables I'm going to talk of now, negative dx over x plus 1 minus u squared over u cubed plus u du is equals to 0. So we can now integrate both sides. What will we get? Integrate this, and also this. So the question is, let's work out these integrals this side. What is the integral of negative dx over x? That should give us negative ln x. What about the integral of 1 minus u squared over u cubed plus u du? Is the same as the integral of 1 minus u squared over, I can see u is common in the denominator, then u squared plus 1 du. So look at our denominator is a product of two factors, a linear factor and a quadratic factor. So what I'm going to do here is to use partial fractions decomposition. So we are going to say that let 1 minus u squared over u into u squared plus 1 be equal to a over u plus bu plus c over u squared plus 1. Or if I cross multiply by the LCM, I'm going to get a times u squared plus 1 plus bu plus c times u is equals to 1 minus u squared. So this equation is true for whichever value of u that I choose. So I'm going to say, if I put u is equals to 0, what do we get? Put u is equals to 0. In that equation, we are going to get a plus, of course, the other one is 0, so a is equals to 1. Let me rub this. Where this u, you put 0, so we simply get a is equals to 1. Any other value of u, let's use negative 1. Put u is negative 1. That means we'll have 2a. So negative 1, that means we'll have plus b minus c is equals to 0. But you know a is equals to 1. So this simply means that b minus c, replace a by 1. So that will be equal to negative 2. I can call this equation 1. Remember, where there is a, I've substituted 1. So I'll have 2 plus b minus c is equals to 0. And you take 2 to the right-hand side, that becomes negative 2. Then what about if I substitute, let's see, put u is equals to positive 1. What do we get? It will be 2a plus b plus c is equals to 0. Or if I substitute a, I'm going to get b plus c is equals to negative 2. So this equation 2. When you solve those two equations simultaneously, equation Roman 1 and 2, if I add them, I'm going to get 2b is equals to negative 4. And so therefore, b will be negative 4 over 2, which is negative 2. Now, when b is negative 2, what do you think will be c? C will be equal to 0. So that integral, this integral can now be written as, remember here, you can just say therefore, negative ln x plus the integral. Let me replace a and b here so that we know the new fraction that we need to integrate. A is 1, so that is 1 over u. B is negative 2, so minus 2u over u squared plus 1 du is equals to the integral of 0, which is, let me just write integral of 0. So this means that negative ln x plus ln u, because here this ln u minus ln of u squared plus 1 is equals to, everything is log on the left hand side, so even the right hand side, let's call it ln c. Then you apply the laws of logarithms to combine this. Remember, this can be written as ln of x raised to negative 1 times u divided by u squared plus 1 is equals to ln c. So you can say, or x raised to negative 1 times u over u squared plus 1 is equals to a constant. Now, let me not use c because already we have the constant c. Instead of using c, we can change it to k because already we have c in the given family of curves. So where there is c, let's just replace this by k, even here, even here. And finally, replace u. So we write put where we have u should be y over x. So this means that x raised to negative 1 times y over x over y squared over x squared plus 1 is equals to k. And if I simplify, this can be written as y over x squared, that's the numerator. Denominator, it is y squared plus x squared over x squared is equals to k. So you see the x squared in the denominator will cancel with this other one. So you can write or y is equals to k times y squared plus x squared, or x squared plus y squared is equals to k1, a constant, times y. So what you have found here is the orthogonal family. This is the orthogonal family that we needed. And you can also sketch it. Look at the one we started with, the one we are calling F, or the one that we are given. This is what we are given. You can't be able to sketch this. This is simply equation of a circle. You can write in the general form. And even the other one that we have found is still equation of a circle. We can also write that in the general form. So let me sketch so that you see the sketch. Let's start by writing F. That was x squared plus y squared is equals to cx. This means this can be written as x squared minus cx plus y squared is equals to 0. If I complete the square in the x squared, what will I get? I'm going to get x squared minus cx plus a number, call it p, then minus p, then I can see plus y squared is equals to 0. So how do we get p? P is equals to b over 2 squared. B over 2 squared, where b is the coefficient of x. So that's negative c over 2 squared. So therefore, it's like now we have x squared minus cx plus, now when you square that you get c squared over 4. Then we have to subtract c squared over 4 plus y squared is equals to 0, which you can also write as x squared minus cx plus c squared over 4, then plus y squared is equals to c squared over 4, or x minus c over 2 squared plus y squared is equals to c over 2 squared. So this equation of a circle, center at, let me comment it here. What I've found here, this one is a circle with the center at, what is the point? It is c over 2, 0, and radius is c over 2. Which kind of a circle is that? We'll sketch it. Let me sketch it here. A circle with center, remember c is an arbitrary constant, so this is 0. Radius is c over 2. If you put c is equals to 0, you get the point as at the origin. Let me write here, at the origin when c is 0. What about when c is 1? Simply when c is 2, if c is 2, the center will be 1, 0, and the radius will be 1. Center is 1, 0, radius is 1. So it is this kind of a circle along this kind of a circle. Again, if c is negative 2, you'll find another circle here. As you continue increasing c, this circle will even increase in radius, and even the center will shift. Even the other one on the negative side. So I can have another one. Remember, these are circles. When you draw circles, not ellipse. So the center keeps on changing, even the radius. So those are the circles we're talking about. What about the one that we have found for G? We have said G is such that x squared plus y squared is equals to ky. Again, if you complete the square, this means we'll be talking of x squared plus y minus k over 2 squared is equals to k over 2 squared. K is a real number, can be positive or negative. Again, these are circles with now the center, you can write here, these are circles, center at 0 k over 2, and radius is equals to k over 2. We can also sketch them. When k is 0, we have the origin. When k is 1, we have this kind of a circle. When k is -1, we have the negative y-axis. When k is 2, as you continue increasing k, you'll get this circle, another one this side. So we proceed to increase the k, we get this, and another one this side. So what I've drawn using black is the first family, f of xy is equals to c. And this other one that I've drawn in blue is g of xy is equals to k. So those are orthogonal trajectories. Lastly, let's look at the other part. That's part B. In part B, what are we given? That y squared is equals to 4cx. Y squared is equals to 4c times x. So as usual, make the constant the subject. So this you can as well write as y squared over x is equals to 4 times c. This is a constant. So what we have here will be our f of x, y. This is f of x, y is equals to a constant. So you write let f of xy be equal to y squared over x. I need the partial derivative of f with respect to x. That is negative y squared over x squared. And also partial f with respect to y is 2y over x. So now, what is the ODE? ODE for the orthogonal family. Orthogonal family. So it should be partial f, let me write here, partial f with respect to x dy minus partial f with respect to y dx is equals to 0. If I replace those derivatives, you can write or we got here negative y squared over x squared dy minus 2y over x dx is equals to 0. Now, if I multiply through by x squared, of course, the negative is common, so you can just write or y squared dy plus 2xy dx is equals to, this equation is homogeneous, it is also separable. Let's solve it as separable, ODE. I want to divide through by y, or if I divide by y, I'm going to get y dy plus 2x dx is equals to 0. So this is separable ODE. It is separable. It is also homogeneous. Separable ODE. So we just need to integrate each term to get our general solution. So we are going to integrate 2x dx plus the integral of y dy is equals to the integral of 0. So what do you get when you integrate 2x with respect to x? That will give us x squared. Then here we have plus y squared over 2 is equals to a constant k over 2, so that I can get rid of 2. So you can say, or 2x squared plus y squared is equals to a constant k. What we have found here is a family of ellipse. This is a family of ellipse. And the one that we started with, what was it? This is just a parabola. Look at what we are given. This one is a family of parabola, family of parabolas. And you see, when you talk about parabolas, there are some things you need to mention. So that is the family of parabolas having vertices at the origin and foci on the x-axis. Parabolas with vertices at the origin and foci on the x-axis. So that means those parabolas are orthogonal to this family of ellipses that you found there, and you can also sketch those two families. So that's how to find the orthogonal trajectories. Thank you all for watching this video. Please subscribe to my YouTube channel, that is Professor Francis Okech. When you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, like, and share this video. When you meet next time, you look at other applications of first order ODEs. Bye-bye.